All right, welcome to the deep dive. Today we're going deep on something pretty fundamental to LLMs, large language models.
Yeah.
How do they really make sense of context? Especially when you've got tons and tons of text, how do they pick out what matters?
Mm-hmm.
A big part of that is the attention mechanism.
Absolutely. And it's really at the heart of how these models
Yeah.
understand and process language.
So that brings us to dive today, multi-token attention. We're calling it MTA.
MTA, yeah.
And, the standard attention mechanism, single token attention, it's been a huge
It
success.
really has.
But it's got some limitations, especially when what matters isn't just one word,
Hmm.
but like a bunch of words together
Right.
or the way they're arranged. Ask an LLM something complex, and it's like it almost gets it,
Yeah.
but it just misses some crucial nuance.
Like it's missing a piece of the puzzle.
That's exactly the kind of thing that MTA is designed to address.
It's all about getting those finer points of meaning.
So for this deep dive, we've got a couple of really great resources.
Okay.
We've got excerpts from our internal notes, the All Notes 2025 44 doc that gives us a good overview, a little bit of context, timeline-wise.
Right.
And we've got the research paper itself, multi-token
The
attention.
source material.
Straight from the source, Olga Golovneva and her team at FAIR. That's Meta.
Yeah, a great combination. The paper gives us the technical nitty-gritty, the real evidence,
Yeah.
while our internal notes give us that bigger picture, how this fits into all the LLM progress that's happening.
Our mission today is to really understand MTA, how it works, why it's such a big deal innovation-wise, and what it could mean for the future of LMs. We're going to be focusing a bit more on the academic side of things.
Sounds good?
So let's start with this single token attention bottleneck. You were talking about how standard multi-head attention works at a basic level.
Yeah, sure. So in a transformer model, the first thing that happens is your text is turned into numbers, embeddings we call.
Okay.
And for each attention head, those embeddings are transformed into three types of vectors: queries, keys, and values.
Okay.
And then standard attention calculates a similarity score between each query vector and each key vector. Usually that's just a dot product.
Gotcha.
Then you normalize these scores using a softmax function, and that gives you the attention weights.
Okay.
Basically, these weights tell you how much each key is relevant to the current query. Finally, you use those weights to create a weighted sum of the value vectors. And that sum is the output of that attention head for that specific query token.
Okay, so following you right, it's that one-to-one comparison between one query and one key that can be the problem.
Exactly.
Like, what kind of stuff might get missed in that simple comparison?
Well, the model can only understand the context as well as those individual query and key vectors allow. If the meaning really depends on how multiple words are connected, the relationships between them, then comparing them one by one might not be enough. You lose that higher level relationship.
Like, you might see each word individually, but not get the full picture of how they work together.
Exactly.
And I think the paper gives a really clear example with Alice and a rabbit.
Oh, yeah, that's a good one.
Can you walk us through that? I think it helps make it more concrete.
Okay, so imagine you're asking the model to find sentences that mention both Alice and rabbit.
Okay.
With standard attention, you might have one head that gets really excited when it sees Alice,
Right.
no matter what else is around, and another head might focus on all the rabbit mentions.
Yeah. Yeah.
But the standard attention, in its basic form, doesn't have a way to directly pick out the places where Alice and rabbit are together,
Mm.
like in the same sentence, actually interacting.
So it could pick up on all the Alices and all the rabbits scattered around, but miss the sentences where they're actually connected.
Exactly. To
Interesting.
get that with standard attention, the query vector for Alice would have to somehow already know to look for rabbit nearby.
Yeah.
That kind of encoding, that's complex. It needs a lot of layers and capacity in the model. It's not something that just naturally happens with single token attention.
Right. So it's not built into the system.
And that's what's cool about MTA. It offers a more direct way to multi-token relationships.
So it's like a more sophisticated way of looking at the connections between words.
Exactly.
Okay, that really clarifies the bottleneck. So how does multi-token attention actually solve this? What's the big innovative jump it makes?
The key is that MTA can look at multiple query and key vectors at the same time. Okay?
It doesn't just compare individual words, it considers the relationships between groups of them when deciding where to focus.
So it's not just one-on-one anymore. It's like a whole group conversation.
Yeah, that's a good way to put it.
It allows for a much better understanding of context because it's going beyond just single words.
So how does it actually do that? What are the building blocks, the architecture that makes that happen?
MTA takes the standard multi-head attention and adds three key components: key query convolution,
Okay.
head mixing convolution,
Right.
and group normalization depth scaling.
Okay.
And these work together to allow the model to consider these more complex relationships.
Okay. Let's take them one by one. Starting with key query convolution. What's the main idea behind using convolution here?
So with key query convolution, we're applying convolutional operations directly to the attention mechanism.
Okay.
You can apply them to the attention logits.
Right.
Those are the scores before the softmax normalization. Or you can apply them to the weights after normalization.
Okay.
And the important thing is these convolutions work across the length of the query and key sequences within each attention head.
So you're not convolving over the word embeddings themselves.
Right.
You're convolving over the attention scores or the weights.
Exactly.
That's kind of a cool idea. What's the advantage there?
Well, it means that neighboring key tokens and even previous query tokens can influence the attention weights for the current pair.
Okay.
Think of the convolution kernel like a little window that slides across the attention matrix.
Mm-hmm.
It combines the values in that window based on its learned weights. Okay, so the model can capture local dependencies and relationships.
So it's not just isolated comparisons anymore. They can inform each other.
Right, like if one query has high similarity with a key, a nearby query might strengthen or weaken that based on its own similarities with nearby keys.
Makes sense. It's looking for patterns in the connections.
Exactly, so the model can focus on these coherent patterns across multiple tokens.
Now, the notes mention both pre-softmax and post-softmax convolution.
Yeah.
What's the academic difference between those two? Like, why would you choose one over the other?
It's a subtle but important distinction. Pre-softmax convolution works on those raw similarity scores
Okay.
before they're turned into probabilities. So the interactions between those multiple tokens happen in a space where the relative importance isn't decided yet.
Interesting.
It's like a more complex multiplicative interaction.
Okay.
Post-softmax convolution, on the other hand, applies the convolution to those normalized weights.
Gotcha.
So the influence of nearby tokens gets directly added to the existing attention distribution.
Okay.
It's a more additive form of interaction. The paper mostly uses pre-softmax, and they also use this simplified causal masking approach. Makes it more efficient.
Speaking of that simplified causal masking, can you explain how that works?
Yeah, so implementing regular causal masking directly with convolutions on those logits can be tricky engineering-wise,
Okay.
especially with those optimized CUDA kernels. So they use a clever trick.
Hmm.
They apply the existing causal mask, the one that stops a token from looking ahead to future tokens, twice.
Hmm.
But in between, they set the mask values to 0. It's a little stricter than ideal, but it's much easier to do computationally and still stops info leakage from future tokens.
It's a practical consideration. Sometimes you got to make trade-offs.
Right, exactly.
Okay, cool. So that's key query convolution. Now onto component number 2, head mixing convolution. What's the innovation there? Why mix up the attention from different heads?
So in standard multi-head attention, each head is kind of doing its own thing.
Yeah, they're independent.
Independent, right. Head mixing convolution allows them to talk to each other.
Okay.
It applies convolution across groups of heads. Again, you can do a pre-softmax or post-softmax.
Right.
The main idea is to let the heads share information and amplify or suppress signals based on what the group is seeing.
So it's like teamwork instead of solo efforts.
Exactly. The model can learn more robust patterns this way, integrating different perspectives.
So instead of each head maybe finding a piece of the relationship, they can now actually work together to see the whole thing.
That's the idea.
Very cool.
You divide the heads into groups and then apply a one-dimensional convolution across the heads at each group at each position.
Okay.
That kernel, it learns how to combine the attention from each head in the group.
So it's figuring out optimal way to blend those different perspectives.
Right. For a group of 2 heads, like they show in the paper, the final weight for each mixed head becomes a mix of the original weights of both heads.
Interesting.
It's a linear combination. So the model can learn really complex dependencies between the different types of attention from each head.
So it's not just picking the best one, it's finding a way to combine them.
Right. And in Appendix B, they even talk about how post-softmax head convolution can be seen as making the output projections from a standard attention head more expressive, effectively increasing its rank.
Okay, so it's like giving the model a richer language to describe what it's seeing.
Exactly.
Makes sense. And lastly, we've got group normalization with depth scaling.
Yes.
I get group normalization generally, but why is this particular implementation important for MTA?
Well, group normalization is here for the same reasons it's used in other areas.
Okay.
It helps the gradients flow better during training and makes the learning process stable,
Right.
especially in deep networks. And then adding that layer-dependent scaling factor, like in the differential transformer,
Yeah.
it helps manage the size of the activations as the information moves through the model.
Okay.
That scaling factor usually grows exponentially with the depth of the layer.
Right.
And that can really help with vanishing or exploding gradients. It leads to better training and performance overall.
So this is more about making the training process more efficient and effective.
Exactly. By normalizing the outputs in groups and then scaling based on the depth,
Yeah.
the model stays well behaved during training. And that leads to better learning and better generalization.
Okay, so those are the three big innovations in MTA. Now, another question. Does it actually work? Does it live up to the hype?
Well, the paper gives some pretty convincing evidence. They started with what they called a motivating toy task.
Okay.
It was designed to the limitations of single token attention and highlight what MTI could do.
So they set up a controlled environment to really isolate the effect.
Exactly.
Tell me more about this task. What was the model asked to do?
So they gave the model a sequence of blocks of letters,
Okay.
just random letters,
Right.
and then after the blocks, a set of question letters.
Okay.
The model had to figure out which block contained all the question letters.
Interesting.
It didn't matter what order they were in.
Okay.
And depending on the version of the task, it had to output the whole block.
Right.
Just the first letter
Okay.
or just the last letter.
So it really had to understand that co-occurrence of multiple elements.
Exactly.
You mentioned that standard transformers struggled with this.
Yeah, they found it surprisingly hard,
Hmm.
especially as the number of question letters went up,
Okay.
because with standard attention, you have to cram all those question letters into one query vector
Yeah.
to match it against a block that has all of them. As the number of letters grows, that just becomes too much information for a single vector to handle.
It's like trying to fit a square peg in a round hole. It just doesn't work.
Right. TA aced it.
Okay.
Near perfect accuracy.
Wow. What was the key difference there?
It could use that key query convolution to gather information from multiple query tokens.
Right.
Each query focused on one question letter,
Okay.
and then the convolution combined them to find the spots, the blocks, where all the letters were present.
That direct multi-token interaction made all the difference.
Exactly. It really showcased the core strength of MTA.
Okay, so that's a pretty cool demonstration, but let's move on to, the real deal.
Yeah.
How did it perform in large language model training? More complex stuff.
So they pre-trained models with 880 billion parameters using the Slim Pajama dataset.
Okay.
And they compared MTA against standard transformers
Right.
and also against models using the differential transformer architecture on different validation sets. The MTA models consistently got lower perplexity scores.
And just a reminder for our listeners, a lower perplexity means the language model is better at guessing the next word.
Yeah,
So it understands the structure of language better.
exactly.
So that's a good sign already.
And what's really interesting is they got those improvements even when they only applied key query convolution to a quarter of the layers.
Oh, wow.
And NTA did it with fewer parameters than the differential transformer.
So more efficient too.
Right. They emphasize in the paper how important the group normalization with layer scaling is for getting this performance.
So better language modeling, potentially less resources, that's pretty big.
Yeah.
Now, did that improvement in pre-training carry over to downstream tasks?
Yeah, they tested the pre-trained models on a bunch of standard benchmarks.
Okay.
Things like question answering with BullQ, common sense reasoning with PIQA, and general knowledge with NMLU.
Yeah, those are the classics.
And even though these aren't really long context tasks, the MTA models still outperform the baselines in most cases. They got a higher average overall.
That's interesting.
It suggests that MTA is better at focusing on the right info,
Yeah.
and that helps even when you don't have super long sequences. It's a general benefit for understanding.
So it's not just about length, it's about a more refined attention mechanism.
Exactly.
So it's a win-win. Now, how about those tasks that are specifically designed to test long-range dependencies? Like, how well can the model connect information that's far apart?
Well, that's where NTA really shines.
Okay.
They tested on Lambda, which is about predicting the last word based on the whole passage. Needle in a haystack, where you have to find one tiny piece of info in a ton of noise.
Right.
And Bobby Long, which is about reasoning over fact scattered throughout a long document.
So really pushing the limits of how far the model has to look back.
Yeah, and in all those long-range tasks, MTA showed big improvements over the baselines.
That's pretty impressive. I know the needle in a haystack task has become a pretty key benchmark for long context retrieval. How did MTA do there?
really well.
Okay.
It was much more accurate at retrieving that needle, that target information,
Mm-mm.
even when they added more needles and made the context longer.
Wow.
It really shows MTA's ability to grab that specific relevant info, even from a super long and noisy input. And the diagonal structures they found in the learned kernels, which we'll get to in a bit, might be why it's so good at finding those specific sequences.
That makes sense. And on Bobby Long, which tests how well the model can reason over scattered facts, like in a story.
Yeah, on Babylon, the MTA model also performed really well, especially when they added more distracting text.
Hmm.
That means it's better at ignoring the noise and focusing on the key info needed to reason, even if it's far apart.
Okay, so those results really suggest that MTA is a big step forward in handling long-range dependencies.
Yeah, they do.
The paper also talk about analyzing those learned kernels within the key query convolution.
Yeah, it's fascinating.
What did that tell us about how MTA is actually working?
Looking at the weights in those kernels gave some really interesting insights into what kind of relationships MTA is learning.
Okay.
They saw some recurring patterns. Sometimes the kernels look like an identity matrix,
Mm, mm,
which
mm.
means the model is still using that direct single token similarity in some places,
Okay.
but they also found diagonal structures. A lot of them,
Hmm.
they think those diagonal patterns help the model boost attention for matching sequences of tokens.
Interesting.
And that might explain why it's so good at needle in a haystack.
Right, because the needle is a specific sequence of words.
Exactly, like that magic number they use in the task.
Cool. What other patterns did they see in those kernels?
They found some that seemed to do a kind of priming,
Okay.
where attention key token was stronger if previous queries had already paid attention to it.
Mm.
Like it's remembering what was important before.
Yeah, keeping track of the important stuff.
Exactly. That could be how it focuses on important things as it processes long sequences.
Makes sense.
And they also found edge detection kernels.
Okay.
These seem to focus on the beginning and end of key token sequences that already had high attention.
Like marking the boundaries of the important parts.
Exactly. That might help it figure out the boundaries of the relevant parts of the text.
Interesting. So it's not just about what to attend to, it's about understanding the structure of what it's attending to.
Right.
And how about the kernels in that head mixing convolution? Did they see similar patterns?
Actually, those were simpler.
Okay.
Common patterns were kernels that were basically an identity matrix, but scaled up or down.
Mm-mm.
So they were mostly adjusting how strong the attention from each head was.
Okay.
They also found some that did a contrast thing,
Mm.
subtracting the attention of one head from another.
So it's figuring out which heads are giving complementary information or maybe even conflicting information.
Right. That means head mixing helps the model learn which parts of attention are useful together and which ones maybe disagree.
It's a mom balanced view.
Exactly. And they noticed that without the group normalization, those scaling factors in the head mixing kernels tended to get bigger the deeper you went in the model,
Hmm.
maybe to compensate for the lack of normalization.
So those deep layers might need to shout louder to be heard.
Yeah, you could think of it that way.
Cool. So the paper also had ablation studies?
Yeah.
Where they took out or changed parts of MTA to see what happened.
Right.
What were some of the main things they learned for that?
Those studies really showed how important the of MTA are.
Okay.
For example, even using key query convolution in just a few layers, like two, could still improve performance.
Hmm.
And it was helpful to initialize those kernels with an identity matrix
Okay.
that seemed to help with training and lead to better results.
Makes sense. Starting from a neutral point.
Right. They tried different kernel sizes for the convolutions, but they saw similar patterns in the learned weights.
Okay.
And the final performance was pretty close.
So that part's not super sensitive.
Right. But one important thing they found was that the group normalization with that exponential depth scaling is absolutely crucial.
Hmm.
Taking that out really messed up the model's training. It couldn't perform well without it.
So those two things are really key, the key query convolution and the normalization and scaling.
Yeah. They also found that it didn't matter too much in what order the convolutions were applied compared to the softmax. The final perplexity was about the same.
So that's good. It's robust to the specific order.
Right.
Now, like any new technology, MTA probably has some limitations.
Of course.
What are some of the drawbacks they found, and what are some directions for future research?
Well, a big limitation right now is that MTA, that is, doesn't work well with the super optimized attention kernels that are used to speed up standard transformers.
Ah, that's a practical concern.
Yeah. So MTA might be better at understanding, but it could be slower because of the computation.
So it needs more resources.
For now, yeah. A big focus for future research is making it work with those efficient kernels.
Okay, so optimizing the implementation, make it more practical.
Exactly. They also suggest that looking more deeply at those kernel patterns, those identity, diagonal, priming, edge detection structures, could reveal even more about how MTA is processing information.
Yeah, getting a better theoretical understanding of what's going on.
Right. And lastly, they suggest trying MTA with different model architectures, not just transformers,
Hmm.
and even using it for things other than text, like images or audio.
Expanding the scope, that's exciting.
Yeah.
Now, how does MTI fit in with other academic work on attention
They
mechanisms?
talk about that in the paper.
Yeah,
They connect it to two main areas of research. One is about making attention more selective and efficient.
okay.
They call it focusing attention.
Right, getting rid of the noise.
Yeah. Things like sparse max, adaptive softmax temperature, and memory mechanisms fall into this category.
Mm-hmm.
And MTA, in a way, something similar,
Yeah.
like the differential transformer,
Okay.
but it's using this new convolutional approach applied to the attention itself.
So it's a different tool for the same job.
Right. The other related area is work that combines convolution with attention.
Yeah.
Convolutions are already used in vision transformers and for things like compressing keys and values in language models.
Right.
But MTA is different because it applies the convolution directly to the attention weights or logits.
So it's that direct interaction that sets it apart.
Exactly. It's a novel way to blend these ideas of focusing attention and convolution within the attention mechanism itself.
Okay, so it's building on existing ideas but taking them in a new direction.
Right.
As we wrap up here, any final thoughts on the significance of multi-token attention? Why it's such a big deal, innovation-wise?
I think NT is a really important step forward.
Okay,
It addresses a fundamental limitation of standard attention.
right.
By letting LLMs look at those richer multi-token interactions, it allows them to understand language with more nuance and more awareness of the context.
Mm-hmm.
The results they got really show how powerful this approach is, especially for tasks that involve long-range dependencies and finding specific information.
Yeah, it's definitely making a strong case.
And from an academic perspective, it opens up new ways of thinking about how attention can evolve to capture even more linguistic relationships.
That's exciting.
It is.
So for our listeners, the takeaway is this.
Okay.
Multi-token attention is a really exciting and innovative step forward in how LLMs process information. By allowing them to look at relationships between multiple words at the same time, it opens the door for a more sophisticated understanding.
Especially for complex or long texts.
Exactly.
And that could lead to better performance in lots of different areas, from more accurate information retrieval to better summaries of long documents and understanding complex questions in a deeper way.
Yeah, the possibilities are pretty big. Now, one last, more academic thought for you all to chew on.
All right.
As we keep pushing the boundaries as LLMs, those patterns that MTA's convolutional kernels learn, the identity, diagonal, priming, and edge detection structures,
Hmm.
what do they tell us about how these models understand meaning?
Yeah,
How they process information?
that's a good question.
Could these kernels be a new way to look inside these increasingly powerful systems?
Interesting.
It's a fascinating area for more research, and I encourage you to dive into it if you're curious. Thanks for joining us for this deep dive into multi-token attention.
Thanks for having me.
All right.
It's been great.
Until next time.
Yeah, see you then.